Yes, hello there. My name is Maclean Leah Bialy, and I'm presenting model selection part 2. We're working on a project whereby we want to do a hair scalp analysis, or call it scalp condition detection. So we had the last time we used it, there are two models, one called YOLO and another one called FASTA. RCNN. So this time we trained a model called real-time detection transformer model. Call it the RT-DET-R. So this one is a powerful real-time object detection model that combines the strengths of CNNs and transformers in an efficient design. So we saw that there are some models which use specifically CNNs, that's the convolutional neural network, and there is what we call a model that uses just a transformer. So now here comes in a model that uses both. So that makes it gives it an advantage over other models. So this one predicts bounding boxes and classes without any slow post-processing, making it perfect for fast and accurate analysis. Yes, for the fact that we are working with object detection, we want to know the boundaries of the regions which are having the scalp conditions. So it will mean that for every object that will be detected, there will be, or it will be encircled, or it will be surrounded by, or enclosed in a bounding box. So this is it directly predicts the bounding boxes and any classes without any slow post-processing. Yes, so for it doesn't need to go into processing and stuff. It directly goes into process. It directly predicts the information or the results without need of processing too much. So in our application, we had to fine tune our real-time detection models so that we could be able to detect and localize the different regions and conditions on the scalp. So looking at our next part, we see that the real-time detection transformer has this model architecture whereby the first layer is the input image, and this is where the image of the scalp is fed into the model. Then from that, we are having the CNN backbone. So this one is like the eyes of this model. It sees the whole image, or yes, the whole image, the surface of the image, and it can be able to learn new features. It can be able to see the edges of the scalp, and it also creates shallow detailed maps and deep semantic maps. So from the backbone, we move on to the hybrid encoder. So the hybrid encoder has this attention intrascale feature interaction. So this one, it looks at the other features in the same scale. If you're having maybe a bounding box which is having very small tiny things, call them flecks, then we can be able to say that maybe the person is having dandruff. So that can be done by the attention intrascale feature interaction. Then we're having CCFM. This one is cross-scale channel fusion module. So this one helps us to detect, it helps us to combine the features which are in the different scales together and put a relation onto them to see how they are related, so that we can get a final result from this scalp or the image which has been sent. Then from there, we get these features, and they tell us hybrid encoder decouples intrascale and cross-scale processing for speed and accuracy. So from the hybrid encoder, we move on to the IOU. This is intersection over union aware query selection. So this one selects a fixed number of high quality features from the encoder output. So after getting the different the results from the hybrid encoder, we push the results into the intersection over union aware query selection. So this one selects the fixed number of high quality features. It selects the best features so that it can be from the encoder output. Then from the encoder output, we move on to the transformer decoder. So this one, it uses auxiliary prediction heads on intermediate layers. So it iteratively refines object queries into final predictions. So this one gets the best features, the high quality features which had been gotten from the hybrid encoder. It gets them from the intersection over union area query selection, and then it refines those object queries into final predictions. So those final predictions will be the ones which will be pushed into the prediction heads, and the prediction heads will get that direct predictions. So as it gets these direct predictions, there will be no post-processing. As you said, in the real-time detection model or the real-time detection transformer model, there is no post-processing, and this one makes this model faster than other models. It puts it on at that advantage. So from that, we say that the real-time detector takes a scalp image and extracts multi-scale features using the backbone. So these features pass through the hybrid encoder, which encoder has the AIFI, that is the attention intrascale feature interaction, then plus the cross-channel feature module, cross-channel fusion module that efficiently fuses details and semantics. Then the intersection over union query, union aware query selection picks the best object candidates, which are refined by the transformer decoder. So the model finally outputs accurate bounding boxes and classes at once, hence no post-processing needed. So in our project, this enables quick and precise detection of scalp conditions. For example, in case we are having in a clinic, and we get to have a patient whose scalp image has been taken, and that patient needs real-time results so that we can be able to get insights, and also maybe be able to give appropriate medications to this person. So this real-time detector would be a very, very nice and very appropriate model to be used at that point. So we're having another one. It's called the Mascara CNN model architecture. So this one uses a CNN backbone as the other one did to pull out important features from the scalp image. So the fact that it has a convolutional neural network, then it is very able to pull important features from the scalp image, talk about the edges, talk about the texture, talk about all the features. So it afterwards creates multi-scale maps with a FPN. This is the feature pyramid network. So feature pyramid, as you hear it, feature pyramid network, it forms very, very many, call them pyramids, or it forms very, very many maps of different objects. So afterwards, it proposes the possible object regions with the RPN, and carefully extracts features using the region of interest aligned. So in our project, we aligned, in our project, yeah, in our project, we trained it to detect and segment scalp conditions like dandruff, as that is our main goal, giving us not just the location but also the exact shape and boundary for each problem area for better analysis. So afterwards, we see the MaxCNN model architecture. It also has the input layer whereby the image of the scalp is uploaded or fed into the model. Then we have the backbone network. This one is like the eyes. So for it, it extracts rich feature maps from the image. Then the feature pyramid network, it builds multi-scale feature maps combining low-level and high-level features. So for it, it is able to detect both small and large objects. For the small objects, we may mean something like flecks, and flecks, these are the small dandruffs which are developing into or on someone's scalp. Then for the large objects, maybe someone is having a big region which has been affected by psoriasis or maybe by alopecia. Then we're having region proposer network. This one scans the feature maps and quickly proposes possible object regions. For the fact that it is a region proposer network, it proposes the regions and the possible object regions. So after the region proposal network, we feed the output into the region of interest align. So this one tells us which region or which specific place or which specific point in the region proposed by the RPN is having the disease. So from that, the output of the region of interest align is pushed into the classification and bounding box. So this one predicts the class of each object and refines the bounding box location. Then I push it into the mask head, which separates branch for pixel level segmentation. So it also generates a binary mask for each detected object. Then after that, we get the final output. Of course, the final output will include the bounding boxes, the class labels, and also the segmentation masks for every object. So this was our architectural discussion. We had to make a comparison between the architecture of the mask CNN and also the real-time detection transformer model. So for the mask, it first extracts it is a two-stage model. So it first extracts image features, then uses the RPN to generate the possible object regions, and then afterwards it refines those regions through separate heads for classification, bounding regression, and also mask prediction. So this design can be very useful. Of course, as long as someone if we need detailed object segmentation, then mask RCNN would be the best for that case. But for us, we need something which is fast and can be practically deployed. And also for the fact that real-time detection transformer model gives a better modern and cleaner architecture, it will be best suited for that. So our real-time detection transformer combines the CNN backbone, which has an encoder and a transformer decoder, then predicts the final object classes and bounding boxes in a single pass using the IOU, that is the IOU aware query selection. So as we see for real-time detection transformer, it is a one-stage process. It undergoes one stage. Then for the mask RCN, it undergoes two. First of all, it extracts the features and also uses the RPN to propose the regions required. Then afterwards, it will have to refine these regions through the separate heads so that we can classify and be able to get the boundary boxes. But for the real-time detection transformer, transformer model, for which it is a one-stage process. It will look at the object, then through using the encoder and transformer decoder, then afterwards it will predict the final object class and bounding box without doing anything. So because of this, we shall have less computation in our model, the RTD DET-R model. We have less computation and we shall have it, the goal is, okay, here we are saying that we chose the RT because our goal is not just strong detection accuracy, but also speed, simplicity, and real time. And here I was using a use case of the fact that if someone walks into the doctor's space and is being checked, then they take a scalp, how long does that person have to wait to get the results? So if we are having this model, if we have deployed this model, then it means someone will get their results there and then without wasting time. And this was an advantage for that. So we are having, these were the results for the mask CNN model. So we had these alopecia, these ones were the classes we were having, and this was the cluster. So we also had this confusion matrix normalized. Then we had this real confidence and the precision recall. So we had these, then these ones were for the real-time detection model. So here we are having something like this. It was very easy. And these were the classes: alopecia, contact dermatitis, folliculitis, head lice, psoriasis, dandruff, dry hair, and low hair density. So these were our classes. So here, this one was showing that we are having very high instances in the alopecia. And for this case, our model trained so much with images having from this. So our data set was kind of imbalanced. But again, we had to fine tune during the process. So these were the diagrams we are having, and this is the conclusion. Thank you for listening. So